Okay, so have you ever tried to remember like a phone number, but you're also trying to plan dinner in your head? And then there's that one song stuck on repeat.
Oh yeah, like you have multiple browser tabs open, but in your brain.
Exactly. Our brains are doing a lot, right? But imagine your computer having to keep track of every single click, every keystroke, every pixel on your screen. Wild, right? That's what we're diving into today, the magic of memory management.
It's true. It's all happening behind the scenes, making sure everything runs without a hitch. It's amazing how we take it for granted.
Right, we use our devices like they have endless memory, an infinite amount of space for everything.
But in reality, it's all a clever illusion.
And that's where source material comes in, right? It's like
Yeah,
getting a backstage pass to see how software actually uses the physical memory in our devices.
exactly. And it all starts with this idea of logical versus physical memory.
Okay, now those words, they sound kind of deep, like what's real and what's just in our minds. But we're talking about computers, right?
Right. So when programmers write code, they're working in that logical memory world. Imagine an architect designing a skyscraper. They're not worried about every single brick and beam right away.
They're focused on the big picture first.
Yes. The layout, the purpose, the overall design. It's like having a limitless canvas, right?
Oh, yeah?
You don't have to think about where every single line of code will physically end up in the computer's memory.
But at some point, you run out of space on that canvas.
Exactly. And in a computer, that canvas is the physical memory, the actual hardware chips with a fixed number of storage spots. And that's where the magic really happens. We write code as if it's limitless, but the system has to translate that into the physical reality of limited memory slots.
So how does it even do that? It seems impossible.
It's like fitting a giant puzzle into a much smaller box.
Mhm.
The system needs to get creative. And it gets even more complicated because a program doesn't just magically teleport from a programmer's brain to the computer's memory in its final form. There's a whole journey involved.
Right, from those lines of code we see in movies to something a computer can actually understand.
Exactly. Our source material goes through this wild ride of code, from human-readable code written in languages like C or Python, to that language computers get machine code. And there are so many moving parts, compilers, assemblers, linkers, each one transforming the code and ultimately affecting where it lands in memory.
So it's not just storing data, it's also managing all those instructions that tell the computer how to use that data.
You've got it. It's like when you move to a new house. You have all your stuff, but you also need instructions for how to unpack and arrange it in the new space. And to make it even trickier, imagine if those instructions changed every time you move something.
Wow, that's a lot to keep track of. It sounds incredibly complex. And this is all happening at lightning speed behind the scenes, right?
Exactly. And this is where things get really interesting and where memory management becomes absolutely crucial.
So we're talking about rearranging massive amounts of information super fast without messing anything up.
It's true, and our source actually had a pretty good analogy for this whole process.
Yeah.
It's called relocation. Imagine having to put a new label on every single thing you own every time you move to a new place.
Oh, wow, yeah. Like relabeling every book, every fork, every sock. That sounds like a nightmare.
It does, but it kind of illustrates what's happening inside your computer right now with memory management. This process of relocation makes sure that every piece of data and every instruction knows where to go, even as things are constantly shifting around.
Okay, so it's like we have a system, a set of rules that lets us pack up and unpack these digital boxes of information no matter where they end up in memory.
Precisely. It's about maximizing efficiency, making sure everything fits without overriding something important.
It's like those super organized people who can pack a month's worth of clothes into a tiny suitcase. You'd think it would be impossible, but they have a system.
Exactly. And just like there are different ways to pack a suitcase, there are different types of relocation for memory management.
Oh, interesting. Our source mentioned two main types, static and dynamic relocation. Can you break those down for us?
Sure. Static relocation is kind of like assigning dedicated parking spots for every single item you own. Each thing has its own predetermined address in memory.
Okay, so everything has its place, decided in advance.
Exactly. But then we have dynamic relocation, which is way more flexible. Think of it like this. Imagine a friend helping you move. They don't decide where everything goes beforehand. Instead, they look at the available space in your new place and find the best spot for each item as they unpack.
So it's all about adaptability, figuring things out on the fly.
Precisely. And that's super important because in today's world, things are changing by the millisecond. We're opening and closing programs, streaming videos, downloading files. Our computers need to be able to adapt to those changes in real time.
That makes a lot of sense. Dynamic relocation sounds like the multitasking master of memory management.
It really is. Instead of rigidly sticking to preset addresses, it waits until a program is actually running before giving it a specific spot in memory.
So it's like, okay, this program needs some space. Let's find the perfect spot for it right now based on what's available.
You got it. That way, memory can be managed super efficiently, even as demands are constantly changing.
This is blowing my mind. I never realized how much was happening behind the scenes every time I click on a button.
It's pretty amazing.
Yeah.
And speaking of behind-the-scenes operations, we have to talk about relocation registers. These little guys are crucial for making dynamic relocation work seamlessly.
Relocation registers. Okay, those sound important. What exactly do they do?
They're like the master organizers of memory addresses. Think of them as labels on those moving boxes we talked about earlier. Instead of listing every single thing inside the box, the label just tells you what kind of stuff is in there.
Okay, so instead of saying, this box contains 20 forks, 12 spoons, and 17 knives, the label just says cutlery. Got it.
Exactly. In this case, those labels, those relocation registers, they hold the starting address for a program or program component in memory.
Ah, okay. So instead of having to relabel every single item when it moves, we just update the starting address and boom, everything inside knows where it is because it's all relative to that starting point, right?
You nailed it.
Yeah.
It's a simple concept, but it's incredibly efficient. And it means that even as programs are loaded and unloaded, moved around in memory, the system always knows where to find everything.
It's like magic, but with, algorithms and circuits instead of wands and spells.
Exactly. But even with this elegant system, there can still be some challenges, like when we end up with lots of little gaps in memory, making it harder to fit bigger programs, kind of like a digital game of Tetris.
Oh, you're talking about fragmentation, right? That's when things start to feel a bit messy.
Yeah, fragmentation. It's like when you've played a great Tetris game for a while, but then you're stuck with those awkward gaps and you can't fit the next piece in.
Exactly. And those gaps in computer memory can cause things to slow down because the system has to work harder to find space for everything.
So it's not just about finding any space, it's about finding the right space for the task at hand.
Exactly. It's like trying to fit different size boxes into a moving truck. You don't want to end up with a bunch of wasted space just because you put a small box in a spot meant for a big one.
That makes sense. So how does the operating system decide which space is right for which piece of information?
Well, remember, those strategies our source material talked about, first fit, best fit, worst fit, they're like different approaches to solving that very problem, right? Like different Tetris strategies for different situations. So walk me through it. How do those strategies work?
Sure. First fit is the simplest one. It's like saying, okay, I need to store this data. Let's just find the first available space that's big enough and we'll put it there.
Got it. Simple and straightforward. What about best fit?
Best fit is a bit more strategic. It takes the time to look at all the available spaces and then picks the one that fits the data most snugly, leaving the smallest gap possible.
Ah, so it's all about minimizing those pesky gaps that cause fragmentation.
You got it. It's like a game of Tetris where you're always trying to create a perfect line. And then we have worst fit, which, as the name suggests, sounds a bit counterintuitive.
Worst fit. So we intentionally choose the worst possible spot for the data. Why would we do that?
It's not as crazy as it sounds. The thinking behind worst fit is that if you always use the largest available space, even if it creates a big gap, you're less likely to end up with a ton of tiny, unusable gaps scattered throughout memory.
Ah, so it's a long-term strategy. Instead of trying to keep everything perfectly organized in the short term, it's more about making sure you have enough big chunks of space available later on.
Precisely. It's like planning your Tetris moves in advance, making sure you don't box yourself into a corner.
This is fascinating. So which strategy is the best one? Is there a clear winner?
Unfortunately, there's no one-size-fits-all answer. It really depends on the specific situation, what the user's doing on their device, the size of the programs they're using, how much memory is available. It's a dynamic process, always adapting to changing demands.
So even with all our fancy algorithms and technology, memory management still involves a bit of art, a bit of intuition.
Absolutely, and that's part of what makes it such an exciting field. It's this constant dance between optimizing for speed, efficiency, and adaptability, all while working with limited resources.
It's like a never-ending puzzle that our devices are constantly solving behind the scenes, and we don't even realize it's happening.
That's a great way to put it, and it just goes to show how much ingenuity goes into creating a seamless user experience.
Yeah.
The next time you click on an app and it opens instantly, take a moment to appreciate the invisible magic of memory management.
Absolutely. It's been amazing learning about all this today. Thanks for the deep dive. I think I need to go clear my head and maybe play a round of Tetris now.
Sounds like a plan. Thanks for having me.
Ever written a line of code and wondered, like, how does this even work?
It really is kind of magical when you think about it.
You click an icon and boom, a program bursts to life. But what's going on behind the scenes?
It's actually a really intricate process.
Well, today's deep dive is all about demystifying that magic. Specifically, the roles of linkers and loaders.
Which are foundational, really, to how software interacts with hardware.
And trust me, it's way more interesting than it might sound.
Oh, absolutely.
Even if you're not a programmer, understanding this process reveals a lot about how computers, think.
Exactly. I like to use the analogy that when you write code, it's in a language that humans understand.
Right.
But computers need instructions in their own language, which is machine code.
So it needs a translation.
Precisely. And that's where the compiler comes in. The compiler takes your source code files and converts them into what are called relocatable object files.
Relocatable.
Yeah, imagine your program needs to store a value in memory, right?
Okay.
The compiler might initially assign it a temporary address.
Kind of like a placeholder.
Exactly. Placeholder.
Yeah.
And then the linker steps in later and gives it a final specific address in the executable file.
Huh. So why is that relocation process so important?
Well, code and data need those fixed addresses to function correctly. If the code wasn't relocatable, the linker wouldn't be able to do its job.
Okay, so the compiler translates and the linker assigns addresses, but how do all these different object files actually become a program that you can run?
So think of each of those object files like a separate ingredient. The linker is the master chef that combines them all into a cohesive dish, the executable file.
But it's not just a matter of like dumping everything together, right? There must be some organization involved.
Oh, absolutely. You're right. The linker plays a critical role in making sure everything connects properly. It also incorporates other important components like pre-written code libraries.
What are those? Like pre-made functions?
Exactly. They provide commonly used functions so developers don't have to reinvent the wheel every time.
That makes sense. So it's like having pre-made sauces or spice blends our chef can use.
Perfect analogy. And you know how different ovens might need different dish presentations?
Yeah.
Well, executable file formats also vary depending on the operating system.
Oh, right. Like different operating systems.
Exactly. ELF is common on Linux.
Okay.
PE on Windows.
Okay.
And Mako on Mac OS.
So it's kind of like they're all speaking the computer's language, but with different dialects. Okay, so now we've got our executable file. It's translated, all packaged up.
Right.
But how does it actually go from just sitting there on your hard drive to running?
Well, that's where the loader comes in.
Okay.
Think of it like this. You got this amazing complex recipe,
Okay.
but it's still just, ink on paper.
Right.
The loader is what takes that recipe and actually starts the cooking process.
So it's like hitting start on the oven.
Exactly. The loader takes the executable file and puts it into memory where the CPU can access it, execute the instructions. It sets up a dedicated space for the program to run, and this is called a process.
Hold on, a process? What is that?
So imagine you're running multiple programs at once, your web browser, a music player, maybe a game.
Right.
Each of those needs its own isolated space to work in.
Okay. Yeah.
So that's what a process is. It's like giving each program its own little apartment in the computer's memory so they don't step on each other's toes.
So it's not just like one big free-for-all in the computer's memory. Everything has its own place.
Not at all. Each process has its own boundaries, its own resources, keeps things organized, and prevents conflicts. Now, remember those pre-written code libraries we talked about earlier?
Pre-made sauces, yeah.
Exactly, the ones that save time and space. Well, there's an even more efficient way to handle those, and it's called dynamic linking.
Okay.
So instead of including every single library in the executable file itself, which can make it huge,
Right.
we use what are called dynamically linked libraries, or DLLs.
DLLs, okay.
And these DLLs, they're only loaded into memory if and when they're actually needed by a program during runtime.
Oh, okay, so it only grabs them if it needs them.
Exactly. Saves a ton of space because multiple programs can actually share the same DLL.
That's super efficient. Are there any downsides to that?
That's a great question. Generally, dynamic linking is fantastic. It's efficient. It can actually be better for security because if a shared library is updated, every program using it benefits without needing a separate update,
Oh, yeah.
as long as the interface remains the same. But it can sometimes lead to issues you've probably heard of, DLL hell.
DLL hell. That sounds kind of ominous. What is that?
So imagine a scenario where you have a program and it relies on a specific version of a DLL to function correctly. Then another program comes along and updates that DLL to a newer version that's not backward compatible. And suddenly the finished program might stop working.
Oh, no.
And that kind of conflict is what we call DLL hell.
Yikes. It sounds like a headache, but it seems like the benefits outweigh the risks then.
For the most part, yeah. I mean, developers have come up with various strategies to try to mitigate DLL hell.
Okay, good.
It's a testament to how well designed these systems are that, that most people using computers, they rarely encountered these issues.
That's good. So we've covered a lot of ground here. From source code to compilation, linking, loading, dynamic libraries.
We really have.
It's really kind of mind-blowing how much complexity is involved in just like simply running a program.
It is, and we've only really scratched the surface.
Wow.
But I think just having an understanding of these core concepts really gives you a deeper appreciation for this intricate dance between software and hardware.
Absolutely. Now, I know you mentioned a tool that lets you like peek under the hood of these executable files called readelf.
Yes.
Is that something that like just anyone can use or?
Yeah, so readelf is a command line tool that's available on Linux and UNIX systems, and it lets you examine the structure of an ELF executable file.
So you can actually see what's in there?
You can, in detail.
Wow, that's really cool.
Yeah, you can see how it's divided into different sections, what libraries it's linked against. You can even see the addresses of specific functions in the code.
It's like having X-ray vision, but for software.
That's a great way to put it.
So who would use that, and how would they use that information? So like developers mostly, or?
Yeah, developers can use readelf for all sorts of debugging and analysis, like say a program keeps crashing.
Right.
readelf can help pinpoint if it's because of like a missing library or maybe a section of the executable got corrupted somehow.
Oh, that makes sense.
It's really invaluable for understanding what's going on at a really, really low level.
It's amazing how much we rely on all these processes without even realizing it, you know?
It's true.
Every time we open an app, play a game, even just browse the web,
Yep.
linkers and loaders are working behind the scenes.
They really are. The unsung heroes of software development, I'd say.
Yeah.
They bridge this gap between the code that humans can read and, the intricate language of computers.
Right.
It makes it possible for us to interact with technology in these like seamless, meaningful ways.
It really makes you appreciate all that complexity that's happening under the surface. Like we've uncovered this hidden world.
And that's the beauty of it, There's always more to learn, always more to explore.
Absolutely.
So like next time you just casually double-click that icon,
Right.
take a moment to appreciate that whole dance of compilers and linkers and loaders and like all those lines of code.
It really does make you think about software in a whole new way.
Well, a huge thank you to you for illuminating this hidden world for us.
Happy to do it. It was fun.
It's been a really fascinating deep dive.
Anytime.
And to our listeners, thank you for joining us, and we will be back soon with more fascinating explorations into the world of technology. Ever get that dreaded spinning wheel of doom? Or maybe the message pops up saying low memory. Yeah, we all have. Today, we're doing a deep dive into something we all use but rarely think about, computer memory, and how software engineers has come up with some pretty cool ways to manage it.
It's one of those things you don't really notice until it's a problem, right? Like when was the last time you thought, oh, I'm so glad my computer's memory is working properly?
Probably never. So let's talk about those problems. What's the deal with memory? We've got more memory than ever in our devices, but somehow it never seems to be enough. Why is that?
It's true, right? You buy the latest phone or laptop with tons of memory thinking, okay, now I'm good for a while, but then...
Bam, full again.
Exactly. It's like our hunger for more sophisticated software and apps is never satisfied. Games, streaming, video editing, it all demands more and more memory. And the way memory gets used, well, it can get a little messy. That's where this concept of memory fragmentation comes into play.
Fragmentation. Okay, that sounds a little intimidating.
Imagine, if you will, your computer's memory like a giant game of Tetris.
I love Tetris.
Who doesn't, right? But now imagine you can only drop the blocks in and you can't rotate them. Eventually, you're going to end up with all these little gaps between the blocks that are too small to really be useful. And that's kind of what happens with memory fragmentation.
Okay, so I can see how that would be a problem. Just like in Tetris, all those little gaps add up to a lot of wasted space.
Exactly. And what's even crazier is that research has shown that even in well-maintained systems, you can have up to a third of your memory just wasted in those tiny gaps. That's like having a whole extra chunk of memory just sitting there unused.
That's like finding a $20 bill in your pocket. So how do we get rid of all those memory gaps? How do we make our computers more efficient?
Great question. One of the tricks software developers use is called swapping. It's kind of like when you're trying to make space in a room, so you temporarily move some furniture out into another room.
Oh, like when my family comes to visit and I have to make space. I feel that.
Exactly. So with swapping, the operating system can temporarily move data that's not immediately needed out of the main memory and onto the hard drive. That frees up space in the main memory for the programs you're actually using.
So it's like shuffling things around behind the scenes to make sure everything fits. Okay, that makes sense. But is there a way to like actually organize the memory better, not just move things around?
Yeah, absolutely. And that's where compaction comes in. This is more like when you decide to reorganize your entire closet to get rid of wasted space. With compaction, the operating system actually analyzes the memory and then relocates data to create larger, contiguous blocks of free space. It's like defragmenting your hard drive, but for your RAM.
Ah, okay.
Yeah.
So we've got the Tetris problem. We're swapping things around. We're doing some serious digital reorganization. But how do all these different programs running at the same time share resources without tripping over each other?
Right. We've talked about managing the space, but there's also the question of managing the actual code itself. And that's where dynamic linking comes in.
Okay, dynamic linking. Lay it on me.
Imagine if every time you needed a hammer, you had to go out and buy a new one. That would be pretty inefficient.
Inexpensive.
Totally. So instead, you might borrow a hammer from your neighbor. Dynamic linking is kind of like that, but for software. Instead of every single program having its own copy of every single piece of code it needs, they can share common code libraries.
Ah, so it's like a giant digital library of code that any program can borrow from. And that saves space and makes everything run faster.
Exactly. And the way they actually do this is pretty clever. They use something called a stub.
A stub, like what I get when I buy concert tickets online.
Kind of, yeah. It's basically a placeholder, a small piece of code that says, hey, I need to borrow this function later. And when the program needs that function, the stub tells the operating system to go grab it from the shared library. The Windows operating system uses this extensively with what they call DLLs, dynamic link libraries. These are essentially giant collections of code that any program can use. It's a huge time saver, and it makes software development much more efficient.
So to sum up, our computers are constantly playing Tetris, rearranging furniture, and borrowing tools from their neighbors, all to make sure our digital lives run smoothly. It's really amazing when you think about it.
It really is. And the thing is, these concepts of efficiency and resourcefulness, they don't just apply to computers.
Oh, you're right. I mean, we're constantly managing limited resources in our own lives, right?
Right.
Our time, our energy, even our physical space.
Absolutely. So maybe next time you're feeling overwhelmed by a messy desk or a jam-packed schedule, think about how your computer might handle it.
Yeah. Organize, share, and be resourceful.
Yeah.
Great advice for our digital lives and our real lives. Thanks for joining me on this deep dive. Until next time.
Ever find yourself staring at your computer screen? Like, how is it doing all of this at once? I mean, you've got apps open, music playing, maybe even a video call, and it's silently downloading a software update in the background.
Yeah.
It's kind of mind-blowing, right?
It is amazing.
Well, get ready to decode the magic, because today we're diving deep into paging, your computer's secret weapon for managing all of that digital chaos.
It really is like, imagine, if you will, your computer's memory as just this giant bustling library.
Yeah.
Right?
Okay.
But instead of books, we're dealing with bits of information. And trust me, things can get really messy if you're not careful about keeping it all organized, accessible. That's where paging comes in.
Okay, now I'm really intrigued. So how does this whole paging thing actually work? Is it like some kind of like super efficient filing system, but for all of our data?
Yeah, I think you could put it that way. Picture this.
Yay.
Right? Instead of having bookshelves that are all different shapes and sizes, which, let's be honest, would lead to a lot of wasted space.
Yeah.
Like when you find that one huge empty shelf and it's still too small for your new encyclopedia set.
Oh, the worst.
So instead of that, what we do is we divide everything into these uniform pages. Think of them as those perfectly sized boxes that you use when you're moving. You know.
Okay, I'm with you.
Each page holds a specific amount of data and can fit neatly into any available slot in memory, which you call a page frame.
So it's all about like maximizing space, like those Tetris masters who can fit any shape in the perfect spot.
Precisely, yes. It's all about making sure that every single nook and cranny of that valuable memory space is being used effectively. And you know what? This isn't even a new idea. This has been around since like the 1960s, when computers really started taking on all these complex tasks. It's kind of amazing It's a testament to those early computer scientists that this system is still relevant in our crazy data-driven world today.
Wow. Vintage tech, but it's still going strong, huh? But it makes me think, if we're dividing everything into these pages, how does the computer actually keep track of where everything is? It's not like there's a tiny little librarian running around inside our devices.
Not a tiny librarian, no, although that would be pretty cool.
Yeah.
You're on the right track, though. Just like a library has that master index to locate any book, the computer uses something called a page table. It's essentially a roadmap that links each page of information to its current location, its page frame in the memory.
Okay, so let me get this straight. We've got our data nicely organized into these pages.
Right.
Each page has its own little designated spot on the memory bookshelf,
Yeah.
thanks to the page table.
Exactly.
But what I'm curious about is, how does this system connect to, us actually using our computers?
Oh, that's where things get really interesting. Let's say you are trying to open up that massive video file that you need for your big presentation.
Okay, yeah.
You click on it, and your computer, using what we call a logical address, which is essentially the file name and location that you recognize,
Right.
searches its page table to find the physical address, which is the actual location of those pages in the memory.
So it's like having two sets of addresses, one that we use and one that the computer uses kind of behind the scenes.
Yeah, exactly. You've got it. Think of it like this. You use the street address, which is like the file name.
Right.
And the computer is using its page table to translate that into GPS coordinates.
Uh-huh.
The physical location, the actual memory. And this is happening constantly.
Wow.
Every time you open a file, stream a movie, or even just type a sentence.
It's incredible how much is going on that we have no idea about. It's like our brains just, effortlessly processing information, and we don't have to think about every single neuron firing. But while this paging system seems incredibly efficient, I have a sneaking suspicion it might come with a few trade-offs, right? You kind of planted a seed of doubt in my mind when you mentioned trade-offs, because it can't all be smooth sailing in the world of memory management, right?
You're absolutely right. There's always, a balance that has to be struck.
Okay.
And remember how we were talking about those pages fitting neatly into any available memory slot?
Yeah.
Well, the thing is, sometimes a program's data might not perfectly fill up an entire page.
Oh, I see where you're going with this. It's like when you pack a suitcase and there's always that little bit of space you just can't quite fill.
Yes, exactly.
Yeah.
Like having a couple of blank pages at the end of a notebook and this leftover space. This is what we call internal fragmentation. It's a little bit of inefficiency, for sure, but I like to think of it as, the small price we pay for this incredible organization, this adaptability that we get with this kind of memory system.
So it's like a trade-off.
Exactly.
A little bit of wasted space here and there.
Yeah.
In exchange for a system that can handle, the insane demands of our modern, always connected digital lives.
Exactly.
I'm okay with that, especially if it means my computer runs smoothly.
Right.
But speaking of digital lives, all this talk about memory access makes me think about security.
Oh, yeah.
How does paging play into keeping our data, safe and sound?
That's a great question, and it highlights a really, really critical aspect of this whole paging system. Think of it this way. You wouldn't want just anyone snooping around the restricted section of a library, right?
Right.
We need to make sure that those programs are only accessing the memory pages that belong to them.
Yeah, it's like having different security clearances for different areas of the library.
Exactly.
So how does paging actually do that? How does it, enforce those boundaries?
Imagine there's a security guard
Okay.
standing right at the entrance of each page of memory, and they're checking IDs to make sure that only the authorized programs can enter, right? That's kind of like what that valid bit does.
Okay, break it down for me. What is a valid bit?
Okay, so you can think of it as this tiny little flag that's attached to each entry in the page table. Remember, that's our master index.
Right.
And if that flag is up, that's basically signaling,
Okay.
hey, this page, it's valid, it's accessible to this program.
Okay.
But if it's down, access denied.
Oh, I like
It's
that.
really, really simple, but it is a very effective way to prevent programs from accessing data that doesn't belong to them.
So not only does paging keep our memory super organized, but it's also protecting our privacy and security.
Absolutely.
It really is like the unsung hero working tirelessly behind the scenes.
It is.
But as our digital lives become even more data intensive, and they seem to be every day, I imagine this system is facing some increasing demands, right?
Oh, absolutely. We're talking about this constant flow of information, browsing the web, streaming music, editing photos, all of it. And as we move toward even more data-heavy applications, things like AI, virtual reality, these paging systems, they need to become even more sophisticated.
Yeah, it's like our digital world is constantly expanding and it requires like even more intricate, more efficient systems to keep up.
Exactly.
What are some of the challenges then in kind of like evolving these paging mechanisms for the future?
It's honestly mind-blowing to think about just the sheer volume of data our devices are processing every second.
It really is.
Like, it makes my brain hurt.
And, you know, as we demand more from our devices, faster loading times, smoother multitasking, more complex apps, all of that, it trickles down to the very core of how our computers manage that information.
And paging, as we've been discussing, really sits at that crucial intersection point.
It's like the foundation that everything is built on.
Exactly. And like any foundation, it has to be strong, adaptable enough to really support the weight of our digital lives.
Right.
And as we move into this future of, we're talking artificial intelligence, augmented reality, I mean, who knows what other crazy data-intensive technologies are coming down the pipeline, right?
Right.
But efficient memory management, it's going to be more critical than ever.
So what you're saying is that seemingly simple thing, right, of like double-clicking to open a file, launching an app, it actually sets off this chain reaction.
It really does.
Of these incredibly intricate processes all happening behind the scenes.
Absolutely. And those processes, they have to evolve to keep up with us, with the exponential growth of data that we're creating.
Right.
I mean, imagine a world where, our devices are constantly learning, adapting, processing information in real time.
It's wild.
While seamlessly juggling all of our everyday tasks.
Yeah.
Right. That's the challenge.
Yeah.
And honestly, the excitement of designing, the next generation of these paging systems.
It's so interesting to me to think that something like paging, which has been around for decades, holds the key to like unlocking these future technologies. It's kind of poetic in a way. It is like we're standing at this precipice of a new era of computing. And this like invisible system, this paging system, is gonna be what shapes it. Well, there you have it. A deep dive into the often overlooked world of paging.
Yes.
We started with the depths of your computer's memory, and now we're here.
The future?
The boundless possibilities of the future.
It really is incredible, though, when we think about it.
It is.
How ingenious these computer scientists were to come up with these intricate systems that operate so smoothly that we don't even notice.
Right.
We just get to focus on the fun stuff. Connecting and creating and exploring and all that.
Living our digital lives.
Exactly.
So the next time you open a file, stream a movie, just do anything on your computer and it's running smoothly, take a moment to thank your paging system.
Yes, the unsung hero.
Quietly working its magic behind the scenes.
And as always, keep questioning, keep exploring, never stop being amazed by this incredible world of technology that we live in.
Until next time, happy computing. Ever feel like your computer is doing like a million things at once? Well, it kind of is. It really is. Today's deep dive, we're talking about how computers juggle tons of information.
Yeah.
We're focusing on these things called segmentation and paging. But don't worry, we're not making you take an exam here.
Sure, exam.
We're going for like, aha moments,
Absolutely.
By the end, you'll actually get a glimpse into like this organized chaos that's happening inside your device every second.
Every single second.
So picture this. Computer memory as a gigantic library.
Okay.
And I'm talking billions, trillions of bits of data and instructions, all needing to be stored and accessed. How does the computer find anything in that? It's got to be more organized than my sock drawer, right?
Absolutely. And that's where segmentation comes in. Think of it like dividing that massive library into different sections, right? Like history, science fiction, cookbooks, you name it. Each section is like a segment in computer memory.
Okay, so instead of one giant, overwhelming library, we have these like neatly categorized sections.
Exactly.
I like it.
Yep.
But how does the computer keep track of what's stored in each segment? Does it have a superpowered librarian?
You could say that.
Yeah.
Computers use segment tables, which are like detailed indexes at the back of a book.
Yeah.
So they tell the computer exactly where each segment begins and ends in the physical memory.
Okay.
So if your computer needs to access something in like the music segment,
Right.
it consults the segment table to find the starting address and knows exactly where to look.
Wait, so it's like those old school card catalogs libraries used to have.
Yeah.
But instead of pointing to books, they're pointing to these memory segments.
Exactly.
That's pretty clever.
It's a system, yeah.
So with segmentation, we've basically organized our massive digital library into these well-defined sections. But I'm guessing there's more to the story, right?
Yeah, so segmentation was a good start. But computer scientists realized it could be even more efficient. Think about it. What happens if a segment isn't completely full? You end up with wasted space, like having half-empty shelves in our library, right?
Ah, I see the problem. We've organized our library into sections, but we haven't maximized the use of space within those sections. So what's the solution?
That's where paging comes in.
So what's the solution?
That's where paging comes in. Imagine dividing each of those library sections into, like, identical standardized boxes.
Okay.
Those are our pages.
Okay.
Instead of having books of all different sizes scattered about every piece of information, no matter how big or small, now fits neatly into these fixed-size boxes. These pages are then stored in equally sized spaces in the physical memory called frames.
Okay, so we've gone from sections to pages and frames. It's like we brought in a professional organizer to maximize every inch of our shelf space.
Exactly.
But I have a question. If everything is in these uniform boxes, does it matter where each box goes within a section?
That's the beauty of paging. It doesn't matter.
Okay.
Any page can go into any available frame in memory, regardless of which segment it originally belonged to.
Okay.
Think of it like being able to put any book on any shelf, as long as there's space. We just need to make sure the library's catalog is updated.
So we're not limited by having to keep all the mystery pages together or all the biography pages in one place. That's incredibly flexible.
Exactly, yeah.
But how does the computer keep track of this constantly shifting jigsaw puzzle of pages and frames?
Just like with segmentation, there's a system for that. The computer uses something called a page table, which is like a master spreadsheet that keeps track of where each page is located in physical memory.
Okay.
So if the computer needs to access page 15 from the music segment, it looks up page 15 in the page table to find its current location in memory.
Okay, so we've got these segment tables acting like library catalogs for sections, and now these page tables working like hyper-detailed maps for each page. It's like the ultimate organizational system.
It is.
But, and maybe this is a silly question, but isn't the computer constantly looking things up in these tables? Doesn't all this searching slow things down?
That's a great question. And you're right, constantly looking up addresses in the segment and page tables could create a bottleneck.
Yeah.
But as always, computer scientists found a way to speed things up. Remember how we talked about frequently accessed information? Well, there's a special mechanism called the Translation Look-Aside Buffer, or TLB, which acts like a shortcut for our shortcuts.
The TLB, it sounds like some kind of secret weapon for memory management. Tell me more.
Think of the TLB like a cache of the most recent page table lookups.
Okay.
It remembers the locations of frequently accessed pages, so the computer doesn't have to go through the whole lookup process every single time.
So it's like having a little notepad next to the computer where we jot down the locations of the pages we use all the time. No need to consult the massive page table every time, just check the notepad.
Exactly. And this clever trick relies on a principle called locality of reference. Basically, if a program is using a particular piece of information, it's highly likely it will need to access that same information or something close by very soon.
So the TLB is like having a little shortcut for our shortcuts. It's like remembering where you put your keys instead of searching the whole house every time you need to go out.
Precisely. It's all about efficiency. And the bigger the TLB, the more key locations it can remember, which generally means faster access to information.
That makes sense. A bigger notepad means we can jot down more frequently used page addresses. But there's got to be a limit, right? We can't store the location of every single page in the TLB, can we?
You're right, the TLB is a limited resource, just like the amount of space on our notepad. But it's surprisingly effective because of that locality of reference principle we talked about. Most programs tend to access the same small set of pages repeatedly, especially during common tasks.
So that means the TLB is usually packed with the most relevant key locations, even if it can't hold everything. It's like knowing that you always keep your keys in your purse. You don't need to search every pocket every time.
Exactly. It's a beautiful example of how understanding the way programs behave allows computer scientists to optimize performance, even at a very fundamental level.
This is incredible. We've gone from this image of a massive, chaotic library to a system where every book has its place, every page is accounted for, and we've even got this shortcut system for frequently used items. It's like the ultimate organization dream team.
And it's this elegant combination of segmentation paging and the TLB that allows your computer to handle millions of operations per second, seamlessly switching between tasks, loading applications, and accessing data without you even realizing the complexity behind it all.
You know, I came into this thinking memory management sounded kind of dry, but I have to say it's actually fascinating. It's like peeking behind the curtain and understanding the magic that makes our digital lives possible.
I'm glad to hear that. It's always rewarding to see the aha moments when these concepts click.
Yeah.
Because once you understand the basics, you start to appreciate the ingenuity and creativity that goes into making computers work.
So there you have it, folks. We dove into the inner workings of computer memory, explored the world of segmentation and paging, and even unlocked the secret weapon that is the TLB. Next time your computer seems to be working miracles, you'll have a little more insight into how it pulls it off. But here's a thought to ponder. As we move towards this future of even more data-intensive applications, AI, virtual reality, you name it, will these memory management techniques be enough? Or will we need even more clever tricks up our sleeves to keep up with the demands of the digital world? Something to think about. Until next time, happy computing.